Good morning, everyone. Thank you for being here today. This webinar is being recorded. We're going to post it to our YouTube channel in a few weeks' time. So you are at the ASCE, EWRI, and AFS-BES Joint Committee on Fisheries Engineering and Science. We are super excited to kick off our 2025 webinar series. So this is the first of quarterly webinars that we will have for this year. And before we get started, just a couple of announcements that we'd like to share with everyone. Here we go. So first up, just shout out to the Joint Committee's leadership team, Amy, Mike, and Theo. Thanks for all your good work. And if anybody's ever interested in learning more about the Joint Committee or how you can maybe participate, you're welcome to reach out to any of the leadership team. Or also you can find our website with a lot more information on the address here on the right side. Feel free to use the QR code. It goes to the same place as the actual email address listed in there. And so this, if you want to hit this QR code or go to this email address, you can find so much information on that website. So that includes all of our previous webinars are on YouTube. Well, up to a certain point, our earlier ones we didn't have a YouTube channel for. But there are about 20 of our previous are on there right now. You can get a link to them directly through YouTube. Just search for Joint Committee on Fisheries Engineering and Science, or you go to our website and go to the webinar page, and they're all linked in there as well. One of the things we also do besides webinars is we help organize and kind of keep a conference going, an international conference on fish passage. The 2025 conference is in China this year. It's coming up at the end of the month. So I hope some of you are attending and presenting, and we'll be able to participate in that. The 2026 conference will be at UC Davis, so heading out to the west coast of the US to hit that conference in early May. So one of them, both of them, we hope to see you all there and participating in these conferences. You can get more info on the conferences through our webpage. We do have linked websites under that original homepage for our committee on there as well. A couple other things, there's some resources for training if you're new to dam removal or have new staff on your team. There's quite a few great resources on there. I think up at the top banner, it's a highlight item for resources and training materials are on there. You can find that on our website. We do have a few upcoming webinars scheduled, tentatively scheduled. So we've got Brian Belgraf from Pacific Northwest National Laboratory coming to speak with us in June. And then we've got a slight divergence, not necessarily a technical topic, but what a fish knows. The author of this book, Jonathan Balcom, will be speaking with us in the fall. We will have one more webinar that is yet to be scheduled in early winter 2025. If you normally get announcements for this webinar series, but you didn't get the direct announcement, it was probably because you've been purged from our list. We are not sure what happened, but there were quite a few dozens of people who had been removed from our listing. So we do have a new sign up, a subscribe. So that's also on our website. This is a direct QR code to our subscribe page. On that page, you can subscribe brand new if you want to get direct ones. Some of you probably saw this through LinkedIn or other groups that you're a part of sharing the announcement. But if you want to get direct announcements on the webinar series, on the Fish Passage Conference, or other industry news around this topic, then go ahead and sign up or resubscribe, subscribe there for the first time to get the direct notices. A quick shout out to our webinar task committee members. Appreciate everybody's work in getting these webinars together, contacting speakers, and getting the announcements out. All right, with that, I'm going to go ahead and talk about today's presenter. So I invited Matt to be a speaker today because I read his paper that I've got listed here, Impounded Sediment and Dam Removal, Erosion Rates and Proximal Downstream Fate. So this was a great paper that I read, and I thought it was extremely useful in communicating to some of the regulators in our area about, and even the downstream folks, what's going to happen with the sediment, how long it will take to move, and just that mobilization effect. So I thought it was a really great tool, a scientifically studied phenomenon on how that sediment evacuates from a reservoir. So I really wanted Matt to come in and talk to all of us about it again and add in some extra nuggets. So if you want to read that paper and you haven't, this QR code definitely gets you directly to the paper. You can also Google the title of the paper, and it'll pop up. It's a free download from NOAA. It's a free download on this. So go ahead and get that PDF and take a read when you can. So Matt's not a stranger to our committee. He's presented in the past. So it's been a few years. So we're really excited to have him back. So Matt Collins, hydrologist and geomorphologist for the NOAA's Restoration Center Northeast region. He manages a monitoring program that evaluates habitat restoration project outcomes. Matt also provides science support for restoration project planning and design across the Northeast, United States, and elsewhere, specializing in stream sediment dynamics and climatic influences on stream flows, important for fisheries resources and project design. So with that, I'm gonna end my slideshow, and Matt, hand it over to you. Thank you again for being here.
Okay, well, thank you, Kathy. I hope people can hear me, or at least you can hear me, Kathy.
Sounds good.
Okay, good. All right, so I'm going to just take a second to switch over to my slides. Do people see title slides, sediment releases at dam removal projects?
Not yet.
Not yet.
We
Oh,
see.
that's because I didn't hit share my screen. Sorry. I went part one of a couple of parts. So screen two. Oh, wow. Okay.
There you go. Looks good.
Okay, great. And I want to do one more thing. The pointer likes to disappear unless I do this, and there it should behave better. Okay, so thanks for that nice introduction, and thanks for having me back, and thanks to all of you for joining. So I appreciate the interest in our stuff, and I hope to keep you interested as I go here. So we'll get started. I like to begin with acknowledgments of all the people involved here. Many people over the years. As Kathy said, I'm going to focus the talk on this most recent study and paper, but a lot of this work builds on earlier work. Another dam removal in the same system, as you'll hear in a moment, and then another dam removal yet in a different system. But I'll try to stitch together for you the commonalities over time. Okay. So I like to start with just describing our motivation for doing this kind of work. And it's pretty simple, and it's maybe the motivation for you attending. Sediment management is an important part of dam removal and other connectivity projects. So it matters in these projects kind of in a big way sometimes. And downstream release of stored sediments is cheap and ecologically beneficial if the sediments aren't polluted. So people want to do this. Like it's an attractive option to let go of the sediment. But communities want to know how long will it take for their river to physically recover. And so answering this question was the primary goal of our research at this site and the others I mentioned. For this most recent study, we used the Bloody Dam site in Maryland, USA, to address it. So to do so, we had these objectives. One, we wanted to estimate the stored sediment quantity for Bloody Dam. It was about 10 meters high, and it's on the Patapsco River in Maryland. And the Patapsco watershed is shown here. It discharges directly to Chesapeake Bay in Baltimore. So in addition to estimating the stored sediment quantity, we wanted to also estimate erosion quantities and rates, and also evaluate the downstream fate of the sediment. All of that's part of answering this question that motivated us. How long does it take for the river to recover? So in the next slide, we're going to zoom to our study area, which is this red box shown here on the watershed map. So here's our study area. We've been studying this area a long time, about 15 years, beginning with the Simpkins Dam removal just upstream of the Bloody Dam. That's shown here. It's very close. The Simpkins Dam was removed in late 2010, if I recall right. So since that period, we've had fixed transects at nearly 30 locations upstream and downstream. And I'm going to show an example section, cross-section 9B, for this black rectangle subsection of our study area, which is shown here in the lower panel. So with these cross-sections, we track accretion or erosion of bed sediment through time associated with the dam removal or other sediment transport events that happen during our study period. And when I say bed sediments, I'm referring generally to sands and gravel size sediment. So at the cross sections, we also survey bed sediment grain size. And we do that by employing Woolman pebble counts for coarser grain sediments. And generally, when I say coarser grain, I mean 6 millimeter granules and larger. And we do grab samples that we analyze in the lab for finer sediments like sands. We also do more intensive surveys of the impoundments to create digital elevation models, or DEMs. And we can then difference DEMs taken at different time periods to do things like estimate erosion quantities and rates over time. These are called DEMs of difference, or DODs. And we create these DEMs using traditional survey methods like a total station and a rod, which is how the cross sections are surveyed. But we also create DEMs with structure from motion photogrammetry from cameras mounted on drones. Again, the Bloody site, this is just showing the impoundment area that we're surveying with DEMs. And then finally, we measure discharge and turbidity continuously at gauges upstream and downstream of the dam removal. Catonsville is a word you'll hear throughout the talk for the upstream gauge. It's just above the Bloody impoundment. And Elk Ridge is the downstream gauge. It's about 5 kilometers downstream. So we're measuring discharge and turbidity continuously at these gauges. And the turbidity data track finer sediment fractions that travel in suspension that aren't measured in our cross-section or DEM surveys of bed sediment. And the discharge data help us interpret our survey and turbidity data. And before I move on finally from this slide, I want to note that the data I present today for Bloody Dam are for near-term results through 2021 for the area, again, within the black rectangle you see on your slide. This reaches in the Piedmont physiographic area of the east coast of the United States, which is steeper and more confined than the coastal plain just downstream. So the Piedmont is this whole area here I'm tracing with my cursor, and the coastal plain starts around here. And it gets a lot less confined and a lot less steep in the coastal plain. So here are these data arrayed in time associated with the dam removal in September 2018. And that dam removal period is in the vertical line through both panels. Now, in the upper panel, we have continuous daily discharge measured at Catonsville, the upstream gauge. And we have the daily mean shown in the blue trace. And we have annual peaks shown in red dots. In the lower panel, we have continuous turbidity measured upstream and downstream. So the upstream Catonsville site is in the black circles, very dark, and the downstream turbidity data are shown in the lighter gray circles. And also shown here are green upward facing triangles, which are the dates when we did our structure from motion DEMs, two of which were, you can see, in close succession just after dam removal. That method's really helpful then when you actually can't get out and survey it by traditional methods. And the orange triangles are when we did our DEMs of the impoundment with traditional methods, total station and stadia rod. The orange rectangles show the occurrence and duration of the cross-section, elevation, and bed sediment grain size surveys. So those are all the data arrayed through time. So that's it for the methods, and now to the results, where we'll spend the bulk of our time. Beginning with how we estimated how much sediment was there to begin with. Now, our estimate of the stored sediment quantity was based on a good understanding of the pre-dam valley surface, much of which was exposed by erosion after the dam removal, so we could actually go out and survey it. And that's what you see here in these survey shot symbols, like a tannish color. This is post-removal, where we could actually go out and survey the pre-dam surface that had been exhumed. For areas not exposed, we had elevation estimates for the pre-dam surface from pre-removal probes and cores, and those are these points here in green and in orange. And with these data, we could develop a DEM of the pre-dam valley bottom, and then difference that from a DEM of the stored sediment surface taken just before the removal, and estimate the stored sediment quantity by differencing them. We also had grain size information in many of the cores, and these are the cores shown in the orange squares. And with that, we could estimate the stratigraphy of the stored sediment deposit. And using all that information, we estimated that right before removal, we had about 186,600 cubic meters of stored sediment, 70% of which was sand, and 30% of which was mud size, so like silt and clays. Now, these proportions of sand and mud match estimates made during the pre-removal engineering studies, but our total stored sediment estimate is about 20% less than was estimated in the pre-removal studies. And that difference between estimates reflects a number of things, one of which was a real change in stored sediment quantity between 2018, when the dam was removed, and 2012, when the estimates were made. They also reflect additional data available to us after removal, like the fact that we could go out and actually survey the valley bottom for a lot of the area. So we had, if you're trying to make estimates beforehand, you can't do that. And they just did a different estimation method for extrapolating point data to polygons. So the point here is, when you have a distance in time between your engineering estimates and your actual removal, you can actually have a change in the stored sediment quantity. We also had some methodological differences, but there was a real change in stored sediment quantity. And that's because for these run-of-river dams, sediment storage changes over time. It can get scoured during floods, and it can refill later, either slowly through time or during another flood event. And so if you have a substantial gap between when those estimates are made and when the dam is removed, your estimate might be wrong. And in this case, it was actually conservative in the sense it was protective of downstream interests. The actual amount was less, but it could have been more. And so if you're planning a dam removal and you have dated sediment storage estimates, you might consider taking the time and spending some money to update those estimates. Here I'm just showing a contour map for the mud stratum thickness. The mud stratum was a basal deposit wherever it was found. So that means it's always underlying the sand deposits. And it was thickest, as shown here, thickest near the left bank and in the lower half of the former impoundment. So here's where the dam was. So it's thicker all over here, and it's actually doesn't even exist over on the right bank side. Okay, so now we're going to look at how much of the stored sediment eroded and how fast it eroded. In these two panels, and we're going to spend a bit of time on this, there's a lot to talk about here. In these two panels, we have days since the breach on the x-axis. And so day 0 is the day the dam removal started. In the upper panel, the y-axis has discharge at Catonsville, immediately upstream of the impoundment, with mean daily, again, in the blue trace, and annual peaks as red dots. And now I'm showing also the estimated 2, 5, and 10-year recurrence interval flood thresholds for the site. On the y-axis of the lower panel is the quantity of impoundment sediment remaining in percent. So on day 0, when we start the dam removal, we have 100% of the stored sediment remaining. What you can see right away is that we had rapid erosion of the stored sediment in the first 6 months, or nearly 60% of it, and then essentially no erosion for the next couple of years. And doing some similar studies at other dam removals, this was a pattern we had seen before. And so I'm going to add data from 2 other sites, the Merrimack Village Dam in New Hampshire, which is shown in gray, solid trace, and the Simpkins Dam just upstream, which is shown also in gray, but in dashed. And you can see the same general pattern. Now, when we published the results for the Merrimack Village Dam in 2011, we called this first phase of early rapid erosion process driven. And that's because it's driven by the base level lowering with dam removal and the increased slope that results. So increased gradient it provides the energy, essentially. It was not driven by flow magnitude. However, once a new channel was incised to the base level and widened to accommodate frequent flows and small channel forming flows like 1 to 2 year floods, right? The bankful forming flows. A new phase began that we called event driven, because erosion after that depended on larger floods, generally greater than channel forming size, to access sediments stored more distant from that newly formed channel. And at the Merrimack site, that first large flood was a 10-year event nearly 2 years after dam removal. And I'm showing that here with this orange line pointing up to that curve. And you can see how that reinitiated erosion during this event-driven period. And at the Simpkins site, just upstream of Lodi, we had a 10-year event, just so happens to be, much earlier in the post-removal period. And so that erosion during that event-driven phase was reinitiated considerably earlier in the post-removal period than at Merrimack Village Dam. And then we had another 5-year event a few years later that reinitiated erosion again. Now at the Lodi site, we've had no further erosion in this event-driven phase, and that's because we've had no floods larger than a channel forming size during that time. All floods are like around 2-year size or even smaller since then. Now I'm showing a DEM of difference that shows the total elevation change in the impoundment from the pre-removal surface to August 2021. And you can see that near where the dam was, there was nearly 10 meters of erosion, or about approximately the height of the dam. and a substantial area along the inside bend of the valley that was not eroded. This sediment remains. You can see it here in this inset view. That it's the same image. I just now showing an inset of it where I don't have the DEM covering the actual surface. So that sediment remains, and its height above the new channel means it's likely going to take a large flood or a series of large floods to erode it further. We think it's unlikely to erode by lateral processes, impinging along its contact with the river, mainly because of its position along the inside of the valley meander. So most lateral erosion would be oriented towards the right bank in this kind of situation, the outside bank. And also, its base along the water surface is that mud stratum that I talked about earlier, which has higher cohesion to resist erosion, and it also revegetated rapidly and vigorously after removal, which further limits its erodibility. So we think this remaining sediment is going to be there for a while. It's going to take quite a large event to get it. Okay, so that was upstream and erosion rates, a big focus of that paper in this talk. But we also cover kind of the near field downstream results too, because they're always of interest to stakeholders of these projects as well. So where did the sediment go? Well, it turns out it moved relatively quickly through the downstream reach, with only a few transects showing persistent but modest accumulations on the bed or bars. We also found little evidence for overbank deposition at these sections. Now, why did the sediment move through so quickly? One of the reasons is the physical setting. Recall that these cross sections are in the Piedmont section of the study area, which is relatively steep and confined compared to the coastal plain section downstream. Also, the post-removal months were very wet in this part of Maryland, historically so. Average discharges were well above average at this time in the near term period after the 2018 removal. You can see this in the Catonsville mean daily. It's quite a bit. The averages are quite a bit higher than this time period I'm showing, but also if you look at a gauge much farther upstream that has data back to the 40s, it stands out there too. So it's like I said, historically stands out. So those are great conditions to keep sand moving, right? Interestingly, though, I want to point out, even though average discharges were well above average in 2018 and 19, notice that floods are not. It's kind of fascinating to me. We have this period of some pretty large floods leading up to the removal, and then the floods turn off, but the average flows kind of turn on. All right, so let's just take a look at these sections in more detail, just so you can inspect them and see if what I'm saying is true. Transect 10, you'll see essentially it's a perfect example of what I was describing. Basically, no accretion on the bed. The dashed lines in each cross-section plot are pre-removal, and all the colored lines are post-removal surveys. At cross-section 10, it's pretty much just transit of material through there. We do have some accretion on a bar at 9B, and some of which actually it seems like by March to April 2021, it stays. December 2018, which is the red line, it begins to build, and then it builds a little more and basically stays. So some modest accretion there on a bar surface, but not at 10. If we move downstream, again, looking on the right first, transect 11 behaves pretty well with what I'm saying. Mostly transit of material through the reach. Transect 10B is more like 9B, something about the Bs. Those are the ones that got some modest bar accretion. You can see that builds up, but then progressively erodes through time. and moves on downstream with some modest accretion of the thalweg at 10V. 12 and 13, by the way, you might have noticed I skipped 11B. That's not because it misbehaves and like doesn't show the story I want to show. It's because I only plot these for sections that I have every time horizon we surveyed, and 11B was sometimes difficult to get because of the flow conditions. But here again, you can see this general phenomenon, modest accretions, most of which kind of move through pretty quickly in this near-term period after removal. Getting further downriver towards the Elkridge gauge and where we transition into the coastal plain, we see some persistent accretion on this bar in particular at 14 over time, and a little bit here in the main channel at 15, but again, fairly modest. And that's true also of 16, which is at the very end of our study reach for this study. You recall from the earlier plots, we have sections much further downstream in the coastal plain, but that's for later stuff to come. So the rapid transport of eroded material through the downstream reach is reflected in the evolution of the bed sediment grain size there as well. This plot that I'm showing now shows how the median grain size of the dominant facies at each transect changed through time. And so a red circle is the pre-removal bed sediment grain size survey result, and every gray upward facing triangle is a post-removal survey. Early post-removal is in a small light gray triangle, and they get progressively larger and darker as we go later in time. On the x-axis is distance from the Bloody Dam. And so negative distances are upstream, positive distances are downstream. And this horizontal dashed line delineates sand-sized sediments below from gravel-sized sediments above. And finally, this gray rectangle just indicates the spatial extent of the Bloody impoundment. So you can see that in the first 2 kilometers downstream, generally the sections were dominated by gravel before removal. So most of the red circles are in the gravel range before the dam's removed. And they remained that way after. And in some cases, they got coarser through time after. So not a lot of evidence for the sand that we know came through sticking around very long, or doing it in a way that changed the median grain size. We see more evidence of the sand release further downstream from 2 to 4. So you can see here's where we start in the gravel range. It gets finer, still in the gravel range, but that's an influence of the sand from upstream, and then moves back closer to where it started. You can see that here at 13 as well, also at 14, not so much at 15, kind of just gets coarser. Further downriver, we see it starting in the sand range and actually getting coarser. So we see a little more evidence of the sand, but even there, by the end of the monitoring period, the dominant facies shifts back to a grain size similar to pre-removal. Interestingly, a specific discharge analysis for the Elkridge gauge, which again is right here at the lowest end of our reach, also reflects the relatively rapid movement of the bloaty sediment through this reach. If you're not familiar with what a specific discharge analysis is, it evaluates whether the discharge needed to achieve a given stage, a water stage, changes through time because of changes in channel geometry or the hydraulics at the site. So this plot shows how the discharge required to attain the site's National Weather Service designated action stage dropped during and after the dam removal, right here. I'm showing this with my cursor right here. And that likely indicates increased bed elevation. But it recovered by spring or summer of 2019 to pre-removal levels. And we saw a similar behavior for the site's designated minor flood stage. It drops near after removal, likely reflecting the bed elevation increasing, but then recovers farther out in time. Now, if you're looking closely, you may have noticed that the discharge needed to attain the action stage back on this plot actually dropped a couple of months before the dam removal began. And we think that's associated with deposition from a large flood in May 2018, when we also saw nearby floodplain surfaces had evident sand and mud accretion. So a little bit of a, and this happens when you're studying dam removals, you can get a mixture of things going on. The dam removal happening, but you can also have big floods happening at the same time. And sometimes you have to tease out what's going on. Okay, and finally, recall that 30% of the stored sediment was silts and clays that travel in suspension. So this is where our turbidity data come in and are helpful for understanding that response. And we did see a spike in turbidity just after dam removal at the Elk Ridge gauge that didn't occur at Catonsville upstream. And so that's this gray plot, part of the plot here. And the gray are the circles indicating the magnitude of turbidity at Elk Ridge, and black are the magnitude of turbidity at Catonsville. And you'll see that you have a spike at Elk Ridge that wasn't evident at Catonsville, so it's coming from the dam removal. But this is pretty brief. It's only about 6 weeks, and thereafter turbidity magnitudes really never exceeded what the watershed is capable of producing during floods without a dam removal. And you can see this by comparing the magnitude of post-removal Elk Ridge spikes here in gray and with spikes at Catonsville, which are the black data again. And those are not affected by the removal, either in the pre or post-removal period. And we just don't see spikes that exceed what the watershed can do on its own. And this finding matches earlier work by Tullos and others, including me, I was on that paper as well, that showed how turbidity magnitudes associated with dam removals rarely exceed those of watershed flood events. And there's a lot of reasons for that. Where they do exceed the magnitude of watershed flood events are sites where you're storing many, many years worth of watershed sediment yield. So very, very big dams. Okay, wow, I'm surprising myself with my complicity on the time here. Time to sum up, and then I'll have time for questions. So impoundment erosion at Bloody Dam was two-phased. Early erosion was rapid and substantial, driven by the gradient change. And later erosion depends on flood magnitude and frequency. And we saw that at our two other sites as well. Eroded sediments were transported rapidly through the downstream reach with little storage. And maximum turbidity magnitudes were similar to those produced naturally by storms. And that's because as much sediment as was behind Bloody Dam, particularly the fines amount, wasn't really more than an annual load. And two-phased impoundment erosion has been observed in a variety of dam removal settings and scales, not just the ones I showed here, which were all relatively small northeast dam removals. And so it's been shown at other sites that I'll just give you a sample of in a moment. And we think this indicates its utility for predicting river response to sediment releases. And so, for example, Amy East and others working at the Elwha Dam removals observed very similar phenomena in their data, this two-phase erosion response. It's been seen at check dam removals or partial check dam removals, which are kind of popular in Japan. I'm just giving the title of a paper showing that here. Some folks working in France observed it at the Pierre Glissat Dam removal in central France. And I have another example of a separate check dam removal in Japan where they found something very similar. And it's also been found at other dam removals in the Northeast, which may be less surprising. But for me, at least, it's been rather interesting to see it in some other environmental settings, but also across scales. Like, kind of, it seems almost scale independent as a phenomenon. So with that, I've finished the slides. I'll just point out here, this is that sand behind the Bloaty Dam, and it's sitting atop the mud stratum there on the left side. It's just starting to be visible, that mud layer, which is very thick over there and kind of pinches out as you go to the right bank. So I'll be happy to take questions if there are any.
Yeah, great. Thank you, Matt. This is good. This is such a cool view. I was there for the explosion and got to watch it slowly erode as part of the construction inspection team.
Cool.
So this is great to see the data and the results and putting it all together is just fantastic. So there are a couple questions already loading up. So I'm going to go ahead and just roll to the top of those and read through them, and hopefully we'll have time to get through them all, but we'll do as many as we can in the next 18 minutes. All right.
Wow, that's going to be a lot of questions. 18 minutes. I should have taken longer.
Yeah, make really long answers. All right. So here's the first one. Was the reservoir drawdown to allow for the August 2021 exposed surface surveys? Did you have to do any estimating with a full pool?
The estimates with the full pool were the engineering estimates from 2012. So our estimate of what was there before removal was made after removal. So what we did was after all that, so I showed that plot with where like 60% of the erosion happened and then nothing happens. And that's where we are today, really. Well, that exposed a good chunk of the pre-dam valley surface, and we could go out and survey it. And so we thought we could improve the estimate by doing that, because more than half of the impoundment was now exposed. And then we can use the cores that were taken during full pool for the thickness of that deposit that remained on the left bank. But before removal, of course, people had to rely entirely on cores. And so our estimate, we thought, was better because we just had much better coverage of the real surface you're trying to estimate. I hope that answers the question.
Okay, so the same person, I think this might be a follow-up, says, I think I understood that it is the increased gradient that provides the energy to erode, not driven by the flow magnitude. Do the higher event flows reinitiate the steep slope condition that promotes erosion?
No. So the incision process during and I'm going to go back to that plot. I think it might be useful to look at. The incision process that produces all this erosion is driven by the base level change and the increased gradient at the site. But that gradient gets less through time as you erode up through the impoundment, and to which then that energy gradient basically becomes the gradient of the pre-dam channel. And so then to get further erosion, you need energy from flowing water. But if your flowing water is always in the newly formed channel, it's not going to erode that material. So you need the larger floods basically to occupy larger proportions of the valley to grab sediment through contact, through shear stresses.
All right, next question. Were actions taken to remove silt and sediment before dam removal?
No.
No.
Some sediment was rearranged over on that left bank by the construction activities, but none was taken away and none was added. So it was kind of it was a basically a nat an unnatural but natural sediment, really. Like we released it without any like taking some out. Yeah.
Have you seen higher turbidity at lower design discharges when comparing pre and post removal turbidity?
Can you say that again? I'm not sure I followed that.
Have you seen higher turbidity at lower design discharges when comparing pre and post removal turbidity?
I'm not sure. I don't. I wonder if that's getting at like. Yeah, I'm not sure. I'm not following. I'm not understanding the question. I'll try to keep thinking about it. And
Not, right? Because it's only the higher design flows that are really causing the erosion in the post removal state at this point. So I guess it's asking about the baseline turbidity.
right. Yeah. So if you go back, so the flows were pretty low here, and so we did have higher turbidity because you were allowing the flow to first access that mud stratum. So that mud stratum gets laid down when there's a reservoir pool and there's like quiescent conditions to allow settling of fines. But as the pool volume decreases, the flows through the reservoir become more energetic because there's just less storage. It's less lake-like, and so you don't settle out fines after a while. You only settle sands, and that's why we get a basal layer of mud-sized sediments with sand on top. And when you remove the dam and have the base level lowering and increased energy gradient at the site, it incisors that whole stack. And it's incising all that mud right there at the point of incision and produces that spike. And that may be during a very low flow or moderate flow. But again, once that channel is formed, you need larger design events to do any more erosion, which may get some of the muds, but there's like a feedback mechanism with mud in that, well, number one, it's more cohesive, so it's not as erosive. But number two, it is very conducive with the organics in it as well and the water retention capacities to quick revegetation. And so the mud is less likely to erode even during larger events. The sand is going to be more likely to erode during larger events. So I don't know if that answers the question, but yes, you can have fairly high turbidities right after dam removal, regardless of flow, even with lower design flows.
Okay, this looks like it might be a three-part question, so I'll read all three of them, but if you want me to go back and take one at a time, we can do that as
Okay.
well. Asking for your opinion on the V-star method of sediment sampling. And then, was there hill slope mass wasting of old sediment observed at any of the post-removal sites after the first 6 months? And is the rate of sediment movement considered good, or would we like to rush or delay the movement?
I think that latter question it really depends on like downstream interests and particularly human infrastructure, but also often recreational uses, like is it a big paddling area or whatnot. It just so happens that some of the reasons we studied this site, both the Bloody Dam and the Simpkins Dam and the Merrimack site, was we didn't have sensitive downstream interests. So we could study these sediment releases that were like full out sediment releases. Like we're not removing sediment beforehand. We're not managing sediment anyway. We're just going to let it go and see what happens. But I think the movement through is generally good, and in the sense that it's quick recovery of the system, regardless of interests. People are going to want a quick recovery of the riverbed that they knew, and in that sense, it's good. But but how you do a sediment release very much depends on what your downstream interests are. If you have like a lot of low-lying bridges or whatnot, maybe even small accretions under those bridges is going to make the situation too sensitive. And so you have to consider that in your design. What was part two? I forgot.
Was there hill slope mass wasting of the old sediment observed at any of the post-removal sites after the first 6 months?
Not so much hill slope, but like the stored sediment as hill slope. Yes.
I think that's what they mean. It's in
Yeah,
little
right. Yeah. So yes, you would get some mass wasting, not of this type that people might be familiar with the conduit dam removal in the White Salmon River, I think it was in Washington State, where they had a lot of fines and a rapid dam removal, and you had mass wasting occurring, delivering sediment to the channel in a very fast period of time. And maybe people might be thinking about that. And then number one again,
the V-star method. Your opinion for sediment sampling?
I'm going to have to punt on that and answer that separately. I'm embarrassed because I was part of that, like developing that. And I don't remember exactly V-star. I know it has to do with the ratio of stored sediment volume to the watershed sediment yield, but I can't remember exactly the application.
Okay.
John Major developed it, but I'm happy to, if you can write down the person's email, I'm happy to follow up on that. But
all right,
yeah.
we've got lots of questions, so plenty of other
more ways to fail.
Did the Bloody Dam include a spillway on River Wright?
The whole dam was a spillway.
Yeah, there was a fish ladder on River Wright.
Yeah, but it was a typical low head dam in the Northeast where basically the spillway is to the abutments on either side, and the abutments are right at the edge of the valley.
Yeah, it's an old hydroelectric dam.
So. Oh, good. There's John Major. He's going to bail me out. John, I just haven't been doing much dam removal lately, so I don't exactly recall.
All right. What was the method for continuous turbidity monitoring?
Oh, it was USGS. They were responsible for that, and it was an optical sensor, nephelometer, nephelometric. Yes, nephelometric, which I didn't do it, and so I can't say a lot more than that. But it was a nephelometer.
Great. Do you feel the downstream results could be modeled with the diffuse wave model from the Bureau of Reclamation?
I don't know. I have a lot of confidence in my colleagues at Reclamation, though, so I'm inclined to think maybe, probably. I really don't know the answer. That's just to compliment them.
Was the initial spike in turbidity and subsequent drop in turbidity coincident with the transition from process-driven to event-driven transport?
More or less. It really, that spike really lasted about 6 weeks, which was shorter than the process-driven phase. The process-driven phase, the shift in the curve was more like at 6 months. So there was still some turbidity erosion after 6 weeks, because if you think about the stratigraphy there, it's sand over mud, and that's the banks on both sides, really. And so as you're getting more erosion, as you form a channel, you're getting more turbidity. But when you're incising through that basal stratum of silt, you're getting a lot more turbidity through that incision than you are through lateral erosion occurring later in the process-driven phase. So no, it's not exactly coincident, but it's close. The other thing to remember too is the delineation between the process-driven phase and the and the event-driven phase is a little also dependent on your survey frequency. You know, we have it at a hinge point right here, but maybe this curve would look a little different if we had another survey point here. Maybe it comes down like this, like we see at Merrimack, or maybe it doesn't. It comes out like here. So some of the curve specificity is related to your survey resolution. So it's not like a fixed point in time. I like to make it look like that, you know, like that. It's kind of, you blur your eyes, it's kind of right. But there's a lot of wiggle room there.
Do you have a general valley slope on the project?
Valley slope is, so it depends where you are. I've got to get to my slide to make sure I'm not mixing it up. It is, the Piedmont is a lot steeper, like almost an order of magnitude, and it is, I thought I had it right here. I think it's 0.002 in the Piedmont. I can't find my notes, and it's 0.004 in the coastal plain. So 0.2% in the Piedmont. For the bed gradient, the valley gradient could be a little different, although it's probably similar. Whew, this is like a grilling.
I think people are engaged. This is great. These questions.
I feel like a federal employee justifying their position.
Put it in an email. Sorry. All right. Was any sediment transport modeling done prior to dam removal?
Yes, Yan Tao Sui. Yan Tao Sui, who is many may be familiar with, is an expert in dam removal sediment modeling, and he modeled both the Simpkins and the Bloaty dam removals. And I talk about that in the paper, the comparisons. Like he particularly made estimates for the Elkridge site. Where this, because the Elkridge gauge coincides with this boundary between the Piedmont and the coastal plain. And so that was an area of expected aggradation. And if there was going to be any prolonged aggradation, it would be there. And we covered this in a paper where we validated his modeling for the Simpkins dam removal. And the validation was quite good. He also made estimates at Bloaty for the turbidity. And I believe the turbidity spikes that he predicted, the elevated turbidity period that I showed was about 50% longer. So not bad.
All right. I think this is probably our last question. Depends on how long the answer is. There are numerous questions left, so are you willing to have people email you to do any follow-up on these questions?
I've got a 5 things thing I got to do every week, and I'd be glad to have like a whole list of questions to respond to for a couple of weeks.
Okay, so we'll get Matt's email and put it in the chat. So if any of you who don't get your question answered want to follow up with Matt, sounds like he's very willing. So here's the last question. What was the depth of the in-water cores? Were they above or below the predicted post-dam removal stream bed elevation?
Oh, like, so the cores that we had, like once we had the surface exhumed, did those cores match up pretty well? I think that's the question. Is that right?
I guess they want to know if the cores went below what you estimated that final bed elevation would be. That's what it's
not generally. No, if anything, they were shy usually. Yeah. Yep. There is a lot of vetting of the cores. Yeah. The cores came from multiple sources. Some far back to the 1980s, but those ended up being quite good depth-wise, and they also were ones that had a lot of good driller documentation on stratigraphy. So we took cores wherever we could get them, but some we had to not use because they didn't get to depths that seemed reasonable. So
All right, Matt, thank you so much. Thank you so much for everyone attending. We
you're
hit
welcome.
300, which is the maximum capacity for this style of webinar. So I know some folks got denied entry. So good job, all of you getting in first. But Matt, thanks so much. Obviously, this was a hugely popular webinar. You broke our records. You are the highest attendee webinar in our history. So thank you so much. Like I said, there's probably another 15 questions here. I will send you the chat just so you can see what people are asking, but it will be up to them individually to get these questions to you. So thank you everyone for attending. Thank you, Matt, for presenting. This has been great. Thanks, everyone. We'll see you in a few more months.
Thank you. Have a good day.